we were last time. So we're building this theory where we have 4 possible states of reality. And the theory, kind of the essential feature of the theory, is that we imagine you can never actually know exactly which of these states of reality you're in. So the maximal states of knowledge that you can have are sort of knowing that you're definitely in one of the 2 states, and it's totally random which. So the GPT state space then is just the convex hull of these points. And so clearly this theory violates the no restriction hypothesis because we're sort of explicitly saying the set of allowed states is a strict subset of the logically possible classical states. So we're like taking the classical theory and we're removing parts of it. And my claim was that these 6 states, these extremal pure states of the theory, are going to behave a lot like these 6 states in quantum theory. And to see that, first let's talk a bit about measurements. So you can measure the p property, which just checks if you're on the left or the right of the phase space. You can measure the x property, which checks if you're in the top or the bottom. Or you can measure the correlations between x and p, which tells you if you're sort of one of these 2 or one of these 2 states. And then these 6 extremal states in the theory behave a little bit like eigenstates in the sense that if you're in one of these 2, you always get a definite outcome of the p measurement, but you give totally random outcomes for these 2 complementary measurements, and similarly for these 2 relative to this measurement, and so on. So the probabilities you get when you put sort of extremal states with extremal measurements are always 0, 1, or 1/2. And I claimed that if you do measurement to one property, then you would necessarily induce a disturbance to the complementary properties. So for example, if we start in this state here, where we know the x variable is equal to 0, and we measure the p variable, are we on the left or the right? Well, imagine we get the p equals 0 outcome, so we find that, in fact, in that run, the ontic state happened to be on the left, so it was here. That's what you learn, right, is that the ontic state must have been on the left, and you already knew it was on the top, so now your knowledge is this. This is like Bayesian updating. And this would violate the epistemic restriction, so my claim is that there has to be a disturbance to the x variable. In particular, with probability 1/2, nothing happens, and with probability 1/2, this permutation that flips the x variable happens. After this action, the stochastic disturbance, then we end up in this state again. And we're going to see that this isn't some like ad hoc addition to the theory. This follows from the assumptions we've already laid out. To see that, we need to talk about dynamics in the theory. So reversible dynamics in the theory are just permutations of the ontic states. Here's an example of a permutation. And you can compute from the permutation, from the action on the ontic states, you can compute the action on the epistemic states. So we went through this in the last lecture, that it sort of just rotates these epistemic states in phase space in a way consistent with kind of just classical probability theory. What about composite systems? So when I bring 2 systems together, their state space composes in the boring classical way by Cartesian product. So to specify the full state of a pair of systems, you just have to specify the individual components of the systems. So here's the state of first system, here's the state of the second system. When you put them together, you just list for me all of their properties individually. There's no new properties that appear when you put 2 systems together. So we can index this ontic state space as follows. So now for a pair of systems, we have 16 possible ontic states, because the system A and system B each have 4 possible ontic states. Here, I'm going to label the states of system A on the left as XAPA, so 0, 0, 0, 1, 1, 0, 1, 1. And similarly here for the states of system B. Now you can see it takes 4 bits of information to specify the state of 2 of these toy systems. And so the epistemic restriction we're going to assume, analogous to before, is that you can only know, so you can only prepare or measure 2 of these bits at a time. So it's like you can always have up to half of the information that's there. The other properties then are completely random. So for example, here's a state where you know that the position of system A is 1 and the position of system B is 0. And you know nothing about the momentum. So you see position of system A being equal to 1, that's that means you're in the bottom half of the phase space. And position of system B being 0 means you're in the left half of the phase space. So you're in one of these 4 ontic states. But there's a bit of an extra thing to check here once you talk about composite systems, which is that the marginals on each system individually also obey that epistemic restriction that we already saw. So for example, here's a state where you know 2 bits of information about the joint system. Namely, you know that the position and the momentum of the system A are both equal to 1. And you know nothing about system B. So that satisfies the sort of global epistemic restriction. You only know 2 bits out of the 4. But it violates the local epistemic restriction because you know too much about system A. It's inconsistent with sort of our starting epistemic restriction. So this is not a valid state in the theory. And you can write down, sort of enumerate all the possible states in this theory. Here's an example of 6 of them. So some of these are just products of independent distributions over the 2 systems. So for example, this is the state we saw earlier where you know the position of both systems. This is what it looks like if you know the position of system B and the momentum of system A. This is an example of a state where you know the correlations between the position and the momentum of system A and the correlations between the position and the momentum of system B, but you don't know any of the individual properties, X or P, for either system. So these are all just product distributions where you have sort of independent knowledge about system A and about system B. But you can also have correlations between, you can also know the correlations between system A and system B. So here's a state where we don't know anything about system A, right? You can see that the state of knowledge is consistent with all 4 possibilities for the ontic state of system A. So the position and momentum of system A are totally unknown. And similarly for B, you don't know anything about position or momentum. But what you do know is that whatever the position of A is, it's the same as the position of B, because they're either both 0 or they're both 1. And similarly, you know that the momentum is perfectly correlated. So this is the ontic state, which is like 0, 0, 0, 0. And this is 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1. So you have perfect correlations between both position and momenta of system A and B. This is similar, except that you have perfect anti-correlations between the positions of A and B. And then here we have a state where you know that the position of A is anti-correlated with the momentum of B, and the position of B is correlated with the momentum of A. So you have a bunch of these kind of correlated types of states, and then we have a bunch of product states. What about dynamics on composite systems? Well, because we need to preserve the epistemic restriction for subsystems, it follows that not all permutations represent valid dynamics on a composite system. So for example, imagine that I consider this permutation here. It is a valid permutation, logically speaking, but if we allowed it as a valid dynamics in our theory, it would map this state of knowledge to this state of knowledge. And this state of knowledge we already saw is not a valid state of knowledge, so this would break our theory if we allowed this. So in this theory, the only valid dynamics are the permutations that preserve the epistemic restriction. And now that we've set up all of that for composite systems, we can see where this disturbance comes from. When you measure one property, why does there have to be this disturbance? And in particular, I claim that this disturbance comes about even though this theory is completely deterministic, right? The dynamics are all permutations. There's no indeterminism in this theory. And yet we have this kind of probabilistic disturbance. And the reason is that every measurement is an interaction with a measuring system. And that interaction causes an unavoidably random backaction. So you're actually going to compute this explicitly in a tutorial, but I want to give you the kind of intuition for it. So basically, imagine you have a system S, and you want to measure some property of it, which I'll call QS. So Q could be position, Q could be momentum. And the only way to measure a property of a system is to bring in some measurement apparatus, have the two interact in such a way that some property of the measurement apparatus gets shifted. And here I'm going to take that property to be the position. So this property gets shifted by an amount proportional to the quantity that you want to measure. And then moreover, you need to make sure that at the start, before the measurement, you know the value of that property, and then afterwards you measure the value of that property. So by knowing the value of x before and after the measurement, you can see how much it changed, which then teaches you the quantity that you wanted to know, which is QS. And what you can show is that if you just check over all the different possible permutations allowed in this theory, every permutation that has this property also has a back action from the variable that's complementary to XA to the variable that's complementary to QS. So there's a back action from the position of this system here onto the variable for system S that's complementary to the one that you're measuring. And this variable P here that causes the back action on the system is necessarily completely random and unknown, right? It's okay if there's a back action as long as you know the back action, because if you know the back action, you can just correct it, and then it's essentially as if there was no back action. But here, the back action is caused precisely by the variable that you don't have knowledge of. So there's no way to kind of get out of this catch-22. And so every possible measurement on a system has a back action on the measured property. And so here you can see we're just deriving it from the sort of, it's kind of a pair of facts that makes this happen. On the one hand, it's the fact that these permutations are restricted. We don't have all permutations, only the ones that satisfy the epistemic restriction. So the ones that you need that don't have a back action are not physically possible. And then secondarily, the property that's causing the shift to the system is necessarily the one that's unknown on the measurement apparatus. So that's why there's this unavoidable disturbance when you do a measurement in this theory, even though the theory is completely deterministic. And with that, we now have everything set up to reproduce the mysterious phenomena from earlier. Okay, good. So for starters, we've already seen that this theory has incompatible measurements. And this is more or less just by assumption. There are different measurements that you can do in the theory, but there's no single measurement that tells you everything about the system. But even so, the important thing is that even though you can't measure position and momentum in a single run of the experiment, it's still the case that every system has a definite property for position and a definite property for momentum. So as we sort of said earlier in the course, just because two properties cannot be jointly measured does not mean that they don't simultaneously exist, which is often what people kind of conclude from the Heisenberg uncertainty principle or something like that. Well, that's something that you could believe, but it's not something that's sort of logically necessarily true, and we have an explicit theory that violates that kind of idea. Was there a hand? Okay. And we saw these are those complementary measurements here. This theory also has entanglement, defined in exactly the same way as entanglement in quantum theory, so namely the existence of states that cannot be written as a mixture of product states. So this is not a mixture of any pair of product states in the theory. And yet, the fundamental properties of the system compose via Cartesian product. In other words, there's no holistic, fundamentally connected properties in this theory. The property of a pair of systems are just the properties of system A and the properties of system B. Entanglement, then, in this theory, describes a particular peculiar state of knowledge, not a new way of being. So people often think that a pair of entangled particles are doing something weird, right? They're somehow connected. They're in a different kind of state of reality. But in this theory, this entangled state, well, what's the actual state of reality when I prepare this entangled state? It's either, this point, or this point, or this point, or this point. So the positions in the momenta aren't somehow changed and doing something mysterious. It's just you don't know which one it is in a particular peculiar way. And why do I say it's peculiar? Why is this kind of an unusual state of knowledge? Well, it's unusual because you have complete information about the joint system. Sorry, I shouldn't say complete. I should say maximal. You have as much information as is possible about the pair of systems. This is a pure state in the theory. but you have zero information about system A, and you have zero information about system B. So that is a bit unusual, right? We're used to thinking in a sort of totally strictly classical theory. If you know everything about a pair of systems, then you know everything about each system individually. Here you don't know everything, but you have maximal information about the joint system. And it's like in quantum theory, where if you have a pure state that's entangled, you have no knowledge of the local states because they're going to be in the maximally mixed state. But again, I want to just emphasize, in this theory, entanglement is not a different way of being. It's a different state of knowledge. Another feature of this theory is that we have no perfect state discrimination in this theory. So consider, for example, these two pure states in the theory. Well, even though they're extremal, they cannot be perfectly discriminated from each other unless they're orthogonal. So there's no single measurement in the theory that can tell you which of these was prepared. But again, it's still true that there's no sort of fundamental fuzziness. The system really is in one of these. If you've prepared this state, it's in one of these two. If you've prepared this state, it's in one of these two. The reason that you can't perfectly discriminate these is that both of these ways of preparing the system are consistent with the same properties, namely the properties that you're in the bottom right ontic state. Even if you have complete information about what the ontic state is, it doesn't tell you which of these two preparations was done on the system. And again, just because all properties can't be measured, or just because which state preparation was done can't be measured simultaneously, doesn't mean that there aren't some sort of fundamentally definite properties for the system. What about steering? So steering can be done as follows in this theory. So imagine you start in some particular entangled state in the theory, which I'm going to take to be this one. And now imagine that you measure the position of system B. So that's just checking if you're on the left half or the right half of the phase space. And imagine you get the xb equals 0 outcome, so this left outcome. Well, then you knew initially it was in one of these four ontic states. Now you've learned that it's on the left half, which means you know that it was in one of these two ontic states. That's the Bayesian updating step. But now, as always, measuring system B induces a disturbance on system B. So and in particular, this disturbance is of momentum. So a momentum flip in this picture is just this permutation shown here. And you can see that this permutation doesn't change any of the properties of system A. It's a totally local disturbance on system B. With probability 1/2, this momentum flip happens. With probability 1/2, nothing happens. And so what you're left with is it sort of randomizes within this bottom left half of the ontic state space. So this is the state describing your knowledge if you've done this measurement on system B and you knew that this was the initial state. If you get the other outcome, so if you found that you're on the right half of the ontic state space, well, then you learn you were in one of these two ontic states, and after the disturbance, you know that you're somewhere in the top right. So when you do this measurement, you're either going to steer to this state or to this state. What happens now if you measure in a different basis? So if I measure the p variable of system B here, well, that tells me if I'm in the first and third columns or the second and fourth columns. So if I get the first outcome, p equals 0, then I learn that I was in one of these two ontic states. Now it's the position of system B that gets disturbed. So that's this permutation. Again, the permutation, this disturbance, is only on the measured system. So it's a local disturbance on system B. After the disturbance, you know that you're in one of these four ontic states. And if you got the other outcome, so that you knew you were in this ontic state or this ontic state, then the disturbance takes you to these four ontic states. So now you can see, just like in quantum theory, your choice of which basis to measure, if you measure the position or the momentum, determines whether you steer to one of these two states or one of these two states. And if you interpreted the state, like the quantum state, as a state of reality in steering, then there's a change to the state of reality. But here, in this experiment, there's nothing changing on system A, right? We're measuring system B, so system B will get disturbed, and some properties of system B can change, but the ontic state of the other system, the distant system, doesn't change at all. So we can steer to different ensembles of states, just like in quantum theory, but sort of Einstein, Podolsky, and Rosen's intuitive expectations are exactly true. There's no spooky action at a distance whatsoever. So remember, EPR, when they thought up the steering phenomena, they weren't actually arguing that there's some weird non-local action at a distance. They were saying it must be that the quantum state is not an element of reality. And that's exactly what happens in this theory. These different epistemic states, and also these entangled states, are not elements of reality. The elements of reality are the underlying ontic states. And that was what Einstein, Podolsky, and Rosen were arguing for, that there must be some deeper properties that are not being disturbed and changed. And the quantum state is just a representation of what we know about those properties. And indeed, all the outcomes of the measurements in this steering experiment are predetermined and totally deterministic, because that's the way this theory is set up. It's just that the two systems are initially correlated, and when you have this collapse of the epistemic state in this theory, it's just Bayesian updating of your knowledge together with some local disturbance. Okay, so what about teleportation? Here's how teleportation works in the toy theory. So we start with Alice and Bob sharing some entangled state, which I'm going to take to be this entangled state here, where, again, the positions of A and B are perfectly correlated. The momenta of A and B are perfectly correlated. Now, the measurement that you do between system S and system A is a measurement in an entangled basis. Here's that entangled basis. So we have 4 entangled states that together partition up the full space of ontic states. So we have this green entangled state, which is just the one I just mentioned. Then we have the sort of orange, yellow ontic entangled state. We have the purple entangled state and the blue entangled state. And you can think of these entangled states as follows. So the green entangled state is the one I just mentioned. You have correlated positions, correlated momenta. The yellow one is correlated momenta, but anti-correlated positions. The purple one is correlated positions, anti-correlated momenta. And then the final blue entangled state is the one where you have anti-correlated positions and anti-correlated momenta. So when you do this measurement, you're learning whether the different properties of system A and B are correlated or anti-correlated. But you're learning nothing about the local properties of system A or system S. And so once you do these measurements, well, notice that you know initially that A and B have perfectly correlated positions and momenta. So imagine I get this first outcome and I learn that the positions and the momenta of system S and A are also perfectly correlated. Well, then I know that the positions and the momenta of system S and system B are perfectly correlated. So you already know, in that case, if I get that first outcome, you know that the ontic state of system B is exactly the same as the ontic state of system A. So in that case, you tell Bob, I got the first outcome, and Bob just does nothing. So he does this identity permutation here, because he already knows that his system is in exactly the same system ontic state as S. So however S was prepared, if S was sampled according to some probability distribution, then B will be prepared in a way that's sampled according to that same distribution. If, in contrast, Alice finds that actually system S and A are related by a bit flip of the position, well, then Bob knows he needs to do a bit flip on the position of system B in order to make sure that all of the properties, the ontic state of B, are the same as the ontic state of system S. And if Alice gets the third outcome, if Alice gets the third outcome, then you know that it's the momentum of system B you have to flip. And if Alice gets the fourth outcome, then you flip both position and momentum. And at the end of all this, the ontic states of these two, B and S, are the same. And consequently, however S was prepared, B is now, your state of knowledge about B is the same as what your state of knowledge was about S. Yeah.
So in these epistemic states, I guess we consider these very simple probability distributions over ontic states, right?
Yeah.
Where you're like, you choose some subset and then you take a uniform probability distribution over those ontic states. Is it possible to have a probability distribution that like still has, you know, the property that the information entropy of that distribution is half of like half the bits of your whole thing? That's and I guess like what's the justification for why we don't consider these more complicated probability distributions?
In this theory, we're sort of simply postulating the set of possible epistemic states and then sort of seeing what follows. You could ask for sort of an explanation of like, why is it that those are the only states of knowledge you could have? And the kind of explanation you might want to look for then is, just like we had an explanation for where the disturbance of a measurement comes from, you might hope to give some explanation of why these particular states of knowledge are possible. Like if you went and you tried to build some device that gives you more information about the ontic state, maybe you could derive why that is from some underlying assumption about the dynamics. People have tried to come up with such an argument. It's not easy. So there's not like an accepted answer to that at present. But yeah, for now, it's sort of just an assumption of the theory. OK. So this protocol achieves teleportation in exactly the same way that no matter what way you've prepared system S, you end up with your state of knowledge about system B is going to be exactly the same as your state of knowledge about system S at the start. And in particular, notice that there's 6 different preparations, extremal preparations on system S. So you're communicating to Bob somehow, sort of you're transmitting to Bob these 6 possible states of knowledge. So you're sending log base 2 of 6 bits of information. That's something like 2.6 or something. So you're sending more bits of information than the classical bits, the 2 classical bits that you actually transmitted via this classical communication here. So just like in quantum theory, where you're sending, the mystery was that you're somehow sending more bits than you're actually communicating. Here, you have that same property, and you can see why it happens. So in particular, what you can see is that at no point are you sort of learning those classical bits and sending them. So you never learn the true state of system S or system B. And you're never trying to like learn the properties of how system S was prepared. So all that you're doing is you're starting with knowledge of the relationship between the true states of system A and B, and then you're learning the relationship between the true states of system S and A. And notice that there's only 4 possible true states of system S. And you're not learning what those 4 possible true states are. You're just learning 2 bits of information about the relationship between S and A. And that's all that you have to send to Bob to ensure that S and B are prepared in exactly the same ontic states. What about no cloning in this theory? Well, just like in quantum theory, if you had a cloning map, then, for example, you could take this distribution and you could clone it to 2 copies, or you could take this distribution and you could clone it to 2 copies, which looks like this. But now the overlap between these 2 states is a half, right? You can see that they both overlap on this particular ontic state here, and they don't overlap on the other. So these 2 states have overlap a half, but these 2 states have only overlap in 1 out of 4 of the possibilities. So these have overlap 1/4. And it's not hard to check that there's no permutation that can make 2 distributions more orthogonal. So you can't take these distributions to something more orthogonal. If you wanted to view this as permutations, you should also bring in some kind of fixed system in some prepared, like ready state, so that it's like a 4x4 grid going to a 4x4 grid. But it's still going to have overlap 1/2, getting mapped to overlap 1/4. So there's a no cloning theorem in this theory as well. What about interference? Well, you're going to work this out in the tutorial, but what you're going to show in that tutorial is that you can reproduce the phenomena that we talked about in the Mach-Zehnder interferometer. In particular, you have wave-like behavior, namely interference, where there's a dependence of the output on the phase, and yet you still only have one detector click, so that's the particle-like behavior. You never sort of see the particle appearing in more than one place. And in fact, you're going to even reproduce all those phenomena of the quantum eraser, the delayed choice quantum eraser, etc. So you'll work through that in the tutorial. But I want to give you a bit of intuition for it already. So the intuition is that we have a field theory now. It's the same theory we've been setting up, but the relevant systems are now the modes. So you have sort of one system which is corresponding to the left mode, and another system which is corresponding to the right mode. And each of these modes, each of these systems, has the two properties. These complementary properties are the number of excitations and the phase of those excitations. So it's not position and momentum any longer, but number and phase. And the key point is that both modes have a definite value for each of these properties. It's always got a number variable, which is either 0 or 1. It's always got a phi property, which is either 0 or 1. And because it has these properties, now these modes can carry information regardless of the number of particles in that mode. So in particular, maybe when you send in this photon here, it takes the left path. So what that means is that the number on the left mode is 1, and the number variable on the right mode is 0. Even in that case, there's still a phase property for both modes. So even though there's no particles in this mode, there's still a phase, and it's still got value 0 or 1. And so you could think of it like the one particle excitation takes the left path, the 0 particle excitation, the vacuum state, takes the right path, but they both have a phase variable, and these phase variables will be sensitive to any sort of actions you take. So if you put a phase shifter here, then you're shifting the phase of the vacuum mode, and when those two recombine at the beam splitter, they have the relevant information, they kind of share it with each other, and they use that information to determine whether the excitation goes out the left or the right. So it's the key point here is that sort of the vacuum, the quantum state that's the ground state is not somehow nothing. It doesn't have no properties. It still has fundamental properties, just like any other mode. In particular, it has this phase property, which can carry information. And you'll work that out explicitly and see that it reproduces everything in a simple, local, classical, deterministic way. So you can keep playing around with this theory, and you can show that it reproduces a huge amount of the sort of qualitative types of phenomena that quantum theory has. Monogamy of entanglement, Stein-spring dilations, pre- and post-selection effects, dense coding, key distribution. All of these things are possible within this theory. And it's kind of hard to overstate how important the seeming mysteriousness of things like entanglement and interference have been for the development of quantum theory, right? Like the debates about how to think about entanglement and interference, they've just been a recurring debate for decades, for over a century now. And most of the claims that people have made about those are sort of explicitly disproven by this theory. This theory is a counterexample to the majority of historical claims about why quantum theory is weird. So, if you're trying to argue that it logically follows that there's a multiverse, or indeterminism, or indefiniteness, or non-locality, or holistic properties, or fuzziness, or complementarity, or retrocausality, or anti-realism, or failures of logic, or any of these other things, just by looking at something simple like double-slit interference, or the existence of entanglement, or the fact that you can steer a quantum state via collapse of the wave function, none of these things imply any of these conclusions. It may be that some of these conclusions are still valid, right? You can still believe in these properties. It's not like the existence of a model disproves them. But the point is you can't conclude any of these things from the phenomena. And I think, moreover, once you've seen how simple it is to explain most of these basic things via such a model, you kind of lose any sort of motivation to believe in any of these really radical conclusions. And if you want to look for reasons to believe in kind of more mysterious conclusions like these, you have to go further than these basic phenomena that we've been talking about. So the only weird thing about this model, the only new thing beyond a totally classical theory like the simplicial GPT, is that maximal knowledge is not perfect knowledge. And that is sort of new, right? There is a feature of this model that needs to be explained. Like, why is it that you can't gain total knowledge of the fundamental properties of the system? It's a good question. If we live in such a world, then we want to answer that question. And if you look back at those historical arguments people were making, then you can, that make steering look mysterious or entanglement look mysterious, The reason that those things look mysterious is because they made the implicit assumptions that quantum states are descriptions of reality. Often they assume they're complete descriptions of reality. Right? That was the thing that Einstein was saying we should reject so that we can better understand steering in a simple local way. If you deny the idea that the quantum state is an element of reality, then you can build models like this one. Once you give up that assumption that the quantum state is an element of reality, all of those quantum phenomena become easy to understand. So to me and to many of us, this strongly suggests that quantum states are representations of knowledge rather than representations of reality. So in particular, classical probability distributions, like quantum states, cannot be cloned, cannot be discriminated, can be steered, can be teleported. They compose via tensor product, not Cartesian product. So you have all these analogies. So the way Rob Speckens puts it is that the diversity of these analogies and the quality of these analogies is strong evidence for the view that quantum states are states of incomplete knowledge rather than states of reality. And now just a few side points. So if you want to understand more about this theory, I've kind of just built it up for you by simple description. But if you prefer a sort of more holistic, rigorous mathematical framing of everything, you can define this theory as a sort of symplectic theory on a phase space. And that sort of definition is sort of fully compositional. Here I sort of just, I didn't describe for you what happens if you have 3 systems. But you can define it in a way that sort of just tells you what happens for all numbers of systems, for arbitrary types of processes on those systems. And once you define things in this sort of fully general way, then you can prove that in any odd dimensions, the theory that you've constructed exactly reproduces a fragment of quantum theory. And this fragment of quantum theory is a very famous one called the stabilizer quantum theory. It's really important in quantum information theory. It's basically the theory you get if you only take eigenstates of Pauli operators and transformations that permute those eigenstates of Pauli operators, and then measurements of bases, of the Pauli bases. So it's just a fragment of quantum theory. This theory doesn't reproduce all of quantum theory, obviously. Otherwise, it would be like the final interpretation. We'd all be like, hooray, problem solved. But if you lived in a world that just had these stabilizer bases, then this theory would perfectly reproduce that. And it's a very large subtheory of quantum theory in the sense that it has sort of all those kinds of phenomena, like steering, no cloning, teleportation. You can do most of this interesting quantum phenomena within this stabilizer quantum theory. In continuous variable systems, infinite dimensions, this theory exactly reproduces what's called Gaussian quantum theory, which is, again, it's a very large subtheory of quantum theory. In even dimensions, interestingly, the theory you construct, like the one we've been talking about, was in dimension 2, so that's an example of even dimensions. It doesn't perfectly reproduce the quantum predictions. It behaves a lot like quantum theory, as we saw, but it makes slightly different predictions. So there's some sets of like preparations, transformations, and measurements you can do in quantum theory in even dimensions, which will give slightly different predictions from the ones in this model. So there's this weird dependence on dimension. Yeah.
Okay, just to check, these are like space dimensions, right? Like we are in 3 dimensions.
Here I'm talking about the GPT dimension.
Oh.
So like for a qubit, dimension 4, and for the toy theory, similarly.
Okay, gotcha. Thanks.
If you're defining it on symplectic phase space, I'm assuming that's like on a continuous manifold.
It can be done on a discrete one as well, which is why I'm talking here about this. So that's a nice way of framing it because it can be defined sort of in a dimension-independent way. Yeah.
I guess in like infinite dimensions, do we know if it exactly reproduces quantum theory or?
In infinite dimensions, it exactly reproduces Gaussian quantum theory.
Oh, right.
So
yeah.
a subset of the, of
Cool.
the things. Yeah. Okay, so you might wonder then, can you extend this model to all of quantum theory? Well, I said here, if you extend it in sort of the natural way, then it doesn't reproduce all of quantum theory, just sort of these sub-theories. Maybe, is there some kind of like simple modifications you could do to build a nice theory like this that reproduces all of quantum theory? No. as we're gonna see in sort of the next 3 lectures, there's sort of 3 major obstacles, which we call no-go theorems, which show that if you want to have basic properties that make the model compelling, like locality, then there's just no way you're going to be able to build such a model. And consequently, if you want to identify the phenomena that more deeply challenge our understanding of reality, then at a minimum, they better not be reproducible in a theory like this one. So, as I said earlier, if someone says, oh, it's entanglement or interference, that's what's mysterious about quantum theory. That's why we can't build a nice realist explanation. That's not a good argument. You need to really go to these formal proofs, these no-go theorems, to find what are the genuinely mysterious phenomena. Now you might be, okay, what is the essential feature of this theory that makes it sort of simple and compelling? Well, we're going to return to that question as well. So we're going to kind of generalize away from this specific theory and try to identify, like, what is it about that theory that made it a good model? And consequently, basically, this raises the question of, like, which are the genuinely mysterious phenomena, and how do we sort of rigorously define that? That's going to be what we'll talk about after we see these no-go theorems. If you're interested in this stuff, this is a very easy paper to read, and it kind of just goes through this model, this theory in more detail. And then this paper here also extends this model to the sort of field theory case, which is how you can understand interference. But you're going to kind of work through the essence of the second paper in the tutorial. But they're both hopefully pretty accessible papers, if you're interested. Any questions before we move on? All right. So this brings us to our first no-go theorem. So right, we're in this mindset. We've seen this toy theory. We see that actually, oh, these realist theories can explain a lot more of quantum theory than we thought. Can we try to extend them to reproduce all of quantum theory? This is the first big problem you run into. It's difficult to build a model that preserves locality. So in any non-trivial theory, we know that distant measurements can give correlated outcomes. But we imagine that these correlations arise because of some prior arrangements of the state of reality. Right? There's some pre-existing properties out there in the world, which we call common causes, that lead to correlations for measurement outcomes. Right? So for example, did you and I leave our houses wearing raincoats this morning? That's going to be something, if you measure over many different days, there's going to be a strong correlation between my wearing a raincoat and your wearing a raincoat. That's not something mysterious. It's not some kind of causal influence of me on you or the other way around. There's just some pre-existing common cause, which is it raining or not? And the question is, can quantum phenomena be explained in terms of these kind of local causal influences in the same way that we think about the classical world? Bell's theorem is a proof that this is not possible, at least not in any sort of natural way. So it's a proof that quantum theory, the statement of Bell's theorem is that quantum theory can generate correlations between distant events that are too strong to explain via local cause-effect relationships under some basic assumptions. So imagine, here's the kind of setup of Bell's thought experiment. Imagine that there's some measurements that are chosen and performed at a great distance. Usually we think of 2 parties, Alice and Bob. Alice chooses, she's got some measurement setting here, x. It's like a dial she can turn to measure in different bases, and then she gets some outcome A. Bob has another dial, he's far away over here. He has some measurement setting y, and he has some measurement outcome b. Now, by relativity, all the causes of the outcomes, or of any event, have to lie in its backward light cone, right? So if we put the backward light cones of the 4 relevant events here, we have the backward light cones of x, a, b, and y. So you can see here, just from this sort of light cone structure, which is not showing up normally, that's weird. In any case, from the light cone structure, you can see, for example, that there's no causal influences from either of these variables to either of these variables, right? Because b is not in the future light cone of a, so a cannot be a cause of b, similarly for y. And x is not in the backward light cone of b and y, so there's no causal influences in either direction. That's just from the space-like separation of the measurements done by Alice and the measurements done by Bob, and the assumption of relativity, sort of relativistic light cone structure. However, you could have a common cause that correlates all 4 of these variables. right? Some just pre-existing state of affairs, some properties of some systems way back in the past that at sort of subluminal velocities has some causal influence on all of these variables. That's consistent with the relativistic light cone structure. We often call this common cause a sort of hidden variable that causally influences and sets up these correlations. You can also just think of it as the ontic state of some prior systems, which again kind of propagates over to Alice's side and propagates over to Bob's side and causally influences things. Moreover, of course, the setting variable on Alice's side is in the backward light cone of the outcome on Alice's side. So we expect there will be a causal influence from Alice's choice of measurement to what she observes, right? And similarly, Bob's choice of measurement surely is going to causally influence what he observes. If we moreover assume that these x and y variables are freely chosen, then they're not going to be correlated with whatever systems are being measured by Alice and Bob. So normally we imagine that these choice of settings x and y are done by like a coin flip. So the outcome of that coin flip is not going to be correlated with whatever systems here are being measured by Alice and Bob. People have done even more radical things to make sure that x and y are sort of randomly generated. You could, there's many ways to generate random correlations. Any good way of generating random correlations is going to uncorrelate. It's going to ensure that whatever the local causes of x and y are, they're not correlated with the shared systems between Alice and Bob that are being measured. So this then is the most general causal structure consistent with our assumptions. So this is the causal structure we want to analyze. And I want to just emphasize again that these properties of the system that are being measured by Alice and Bob, the things that are setting up the correlations, are not necessarily observed. Here we're just imagining a, b, x, and y are the observed variables. And Bell's theorem, at least phrased in a sort of modern way, says that the data you observe in these experiments, a probability distribution over AB given x and y, this data that you obtain if you actually go do this experiment in the lab is inconsistent with any such causal structure if you assume that this variable here is just some classical random variable describing some sort of classical properties or the ontic state of the system, and if these variables here depend on each other via classical causal dependencies, by which I mean just a functional dependence or a stochastic dependence. So A depends on x and lambda, B depends on y and lambda in some either functional or stochastic way. Another way of framing, just basically saying exactly the same thing. So this is kind of the circuit you would draw that has exactly the same dependence structure, right? You have a common cause of the two outcomes A and B. So here we have two classical systems which can be prepared in some correlated state. One of them influences the outcome A, the other influences the outcome B. So this is kind of the circuit diagram. And the claim here is that this circuit, where you take these two systems that are generating the correlations, this common cause here, if you take them to be classical systems, then you can't explain all of the correlations you can get if you take these to be quantum systems. So another way to put it, some of the data you can observe in this circuit, in other words, the data that can be generated in a common cause quantum circuit, cannot be generated by any common cause classical circuit. So that's what we're going to prove, and that basically proves Bell's theorem. There are strictly more correlations consistent with this explanation than this explanation. So should we get into the proof? We have maybe 10 minutes. I think we can get pretty far. Okay, so this is, question.
Just wondering, how do you formalize this classical common cause and quantum common cause? In the classical cases, it's like depends on the same random variable, or what's the...
So formalizing what a quantum common cause means is a harder question that we won't say we'll say a little bit about later, but not a huge amount. Classical common cause, that's something we've already sort of defined formally. You can just think of this as a simplicial GPT. So if each of these systems is described by a simplex of possibilities, and this preparation is just a state on a pair of simplicial systems, then that's one way to formalize all this. Another way to think about it is just this is a stochastic process on two classical random variables.
Okay.
Yeah. Another way to think about it is this is just an ontological model where we have an ontic state space here and an ontic state space here, and this is an epistemic state, and this is a some arbitrary stochastic transformation, and so on. So we have kind of a number of equivalent ways of formalizing this, and we've already seen 2 of them. Yeah. Is there another hand? Or? Okay. Okay, so to prove Bell's theorem, we want to start with this assumption that this whole experiment is being described by these classical, by a classical theory, as we just said, a simplicial theory, or just stochastic processes, if you like. And we want to ask what kinds of correlations can be generated in the circuit. Well, let's take the simplest case where x has 2 possible values, a has 2 possible values, and similarly for y and b. So each party has 2 binary outcome measurements, which I'm going to label the possible values of by 0 and 1. The correlations that we want to study are these conditional probability distributions, PAB given xy. And to start to understand which of these are consistent with this diagram, first let's talk about these unobserved systems here. We're assuming that they're classical systems, so we can associate to each one just some ontic state space, or if you like, just some classical random variable. This is just the set of possible states that this system can be in, lambda 1 and lambda 2. And now, if this is a classical theory, a process with no input on 2 outputs is just a probability distribution over those 2 ontic state spaces, right? This is just the epistemic state describing the way that these 2 systems were prepared. Similarly, this process here, it's a process from 2 inputs to 1 output. So it's a stochastic map from these input variables to this output variable. And you can specify that stochastic map by just saying, how does A depend probabilistically on the inputs x and lambda 1? And similarly, how does B depend probabilistically on the inputs y and lambda 2? And now, from this, basically we just compose these using the law of total probability, or equivalently, what we call the classical Markov condition. So the classical Markov condition says, basically you take the different stochastic processes here, you multiply them all together, and then you marginalize over the composed systems. And that is the only, basically any correlation consistent with this causal structure can be decomposed in this way. So in other words, we have this probability distribution over lambda 1, lambda 2. We multiply it by the probability of getting outcome B given y and lambda 2, the probability of A given x and lambda 1, and then we sum over these unobserved lambda 1 and lambda 2s. Again, it's just a form of the law of total probability under the assumption that this is the causal structure. And now the point is this kind of structure, the fact that this probability distribution decomposes in a particular way lets us prove things about it. It lets us prove that not every conditional probability distribution has this form. And we want to investigate those constraints. So the first constraint that's really easy to see is that any probability distribution of this form here has the following property. The probability of B given x and y is independent of x. So it's just equal to some fixed probability of B given y. And intuitively, that's what you kind of expect when you look at this diagram, right? Like, if I think about the probability of B given x and y, well, x doesn't have any sort of causal influence on B. That's kind of immediately sort of evident from the diagram, right? So we expect that there's no dependence of the sort of marginal on B on x. And that's what this statement here is. How do we prove that from this condition here? Well, first, what is the definition of P of B given xy? Well, in terms of this joint object here, P of AB given xy, if you marginalize over A, so you sum these probabilities over A, that's the definition of this quantity that we're interested in. So we're basically saying if you ignore A, then you get just this marginal probability over B given x and y. So what do we get if we sum a PAB given xy of this form here? If we sum this over A, you see that only one of these terms depends on A, right? This term here depends on A. And it's a conditional probability distribution, which means if you sum it over A, it's just equal to 1. So when I do this summation over A, This term here falls out. And now you see, well, there are two terms here that depend on lambda 1. And this one is now gone because we summed over a. So now this summation over lambda 1 here can also be done. So we have a summation over lambda 1. There's a single term depending on lambda 1. This is a probability distribution, and we're marginalizing over one of its two variables. So when we do that, again, we're just left with the marginal probability distribution over lambda 2. So if we sum over a, then it also allows us to sum over lambda 1 in this distribution, and we're left with this expression here. So all we have left is p of b given y lambda 2, and then we have the marginal on lambda 2. And again, we're summing this over lambda 2. So this follows just from two lines of kind of using the properties of probability distributions. So now we know that p of b given xy is equal to this expression here. And you can see that this expression here has no x in it. There's no dependence of this expression on the variable x. In fact, we didn't even need to do that second step, right? It's enough to just notice when you sum over a, this term here goes to 1. And this is the only term with an x in it. So you see that the x dependence is gone. And so pb given xy is equal to p of b given y. And this is called the no signaling condition. It says that if I'm over here, if I'm Bob, and I observe outcome B, I get no information about what the setting was for Alice's measurement far away. And that's kind of common sense, right? If there was some way for the variable x to influence the variable b, or for you to learning b, if learning b taught you something about the variable x that's potentially far, far away, then that would violate relativity theory. You could signal from Alice to Bob no matter how far apart they were. And that's why we call this the no signaling condition, because it just guarantees that there aren't these instantaneous ability to communicate at an arbitrary distance. But it follows from this assumed decomposition of the observed probabilities, which in turn follows from the assumption that this is the causal structure. And of course, there's the analogous condition by symmetry, which is that y does not signal to a. In other words, the probability distribution over a, given x and y, is independent of y. So that's the first constraint that follows, and it's the very simple one. The second constraint, which is a little less trivial, is this constraint here, which is called a Bell inequality. And we will prove that next lecture. So any questions so far on the setup or the no signaling condition?
Just one more quick question. What's the difference between big lambda and small lambda? Which one's a state? Which one's a, I don't know, transformation or something?
So big lambda is the space of possibilities for little lambda.
Oh, okay.
So, yeah, these are like the ontic state spaces. Like, maybe I'm being a little sloppy here insofar as a system is associated with a set of possibilities. So maybe I should have also made this x, a, b, and y capital letters. Like that range over the possibilities. The possibilities are the small variables. And then the things that are like transformations are sort of the boxes or the triangle here. The things that have inputs and outputs are the states, transformations, measurements, etc.